Okay, so I think that's recording the lecture now. Anyway, so probability is number of outcomes you want divided by the number of possible outcomes. So all outcomes, what are all the outcomes here? It's all possible groups of 5 cards. How many groups of 5 cards are there? Right, C52.5. So that's the number of possible outcomes. What we want to know, 2 red and 3 black, right? That's some of the possible outcomes. How many are there of that? So how do I go about calculating that? Well, we have to look at our deck of cards. Decks of cards, there's 52 cards total. That's why we had C52.5. We're picking 5 cards out of 52. We're not worried about the order, so it's a combination, C52.5. And it's divided up in different ways. Half the deck is red cards, half the deck is black cards. So there's 26 red, 26 black. The red cards are hearts and diamonds. There's 13 of each of those. The black cards are spades and clubs. There's 13 of each of those. Number cards, I consider the aces to be a number card. So that's aces. And then you have aces, 2s, 3s, 4s, 5s, 6, 7, 8, 9, 10. And there's 4 each of those, right? Ace of hearts, ace of diamonds, ace of spades, ace of clubs. Face cards, if you actually look at a deck of cards, these cards actually have faces on them. The others have names. So there's, on the jack, there's a picture of a person, queen, kings, there's people there. So those are called face cards. So decks of cards are convenient things for probability because there's lots and lots of ways to slice up a deck of cards. So how many ways are there to get 2 red cards and 3 black cards? Usually thinking about cards as a sequence of things, we want to pick 2 red from the 26 red cards, and then 2 black from the 26 black cards. So how do we pick 2 red out of 26? Well, that's C26 too. We're not worried about the order, so it's a combination. We're picking multiple things, so that's picking 2 things out of 26. A sequence is a multiplication. So first we pick 2 red from 26 red, and then we pick, oh, am I doing 2 red or 3 red? 3 black. And then I pick 3 black cards for my 26 black cards. So that's the number of ways to count how many 5-card hands have 2 red cards and 3 black cards. We know how many total outcomes there are. So this will be C26, 2 times C26, 3 over C52, 5. Great. So that's a way to calculate that probability. And if you actually calculate that and put that in your calculator, that should be 0.325. So about a third of all hands, if you pick the 5 cards at random, will be 2 red cards and 3 black cards. What about 2 4s and 2 queens? Well, you have to keep in mind that we're actually picking 5 cards, right? And I've only specified 4 of them. So we want 2 4s, 2 queens, and 1 other, because we have to have 5 cards. So it's a sequence, right? First I pick these, and then I pick these, and then I pick that. How many ways are there to pick 2 4s, where there's 4 4s all told, and you want to pick 2 of them? How many ways are there to pick 2 queens out of 4 queens? C4 2. How many cards are left? So I need to pick 1 card from 52 minus 8, which is 44 cards. Why am I subtracting off 8? Well, there's 4 4s, there are 4 queens, right? So there's 8 cards, and I don't want to pick one of those 8 cards. I want to pick some other card. So 52 minus 8 is 44 cards. So I need to pick from those 44 cards, I need to pick 1 card. So what are the number of ways to get 2 4s, 2 queens, and 1 other card? Multiply these together because it's a sequence of choices. This times this times this. So the probability, and we usually write that as a P and then a parentheses, and then whatever it is that you want. I want 2 4s, 2 queens, 1 other. And that will be C42 times C42, that's the queens, times C44-1. All divided by C52-5, because that's the total number of groups of 5 cards that we have. And that's a very small number, 0.000609, 0.006. So very few, 6 out of 10,000 times that you pick 5 cards at random from a deck where you get exactly 2 4s, 2 queens, and 1 other card. And finally, what's the probability of getting a full house? Now, full house is 3 cards of one type and 2 cards of another type. So I could have, say, 3 2s and 2 8s, or 3 5s and 2 queens, right? Those could be a full house. So a full house how do you construct a full house? You pick a type, and then you pick 3 of that type, and then you pick a second type, and then you pick 2 of that type. And I'll just draw a line here so that we know that we're working a new problem. So you pick a type, you pick 3 of that type, you pick a second type, and then you pick 2 of that type. It's a sequence of steps. Whenever you're doing a sequence of steps, you multiply things together. So there are 13 types. I pick 1 of them, and then I pick 3 of those 4 cards, so C43. And then I pick a second type. I've already picked 1. I have to pick a different one, so I need to pick 12, and then times C42, and the whole thing gets divided by the total number. So the number of ways to do this process is the numerator. The total number of possible outcomes is the denominator, and this is 0.001441. So less than 1% of the time, if you pick 5 cards at random, you get a full house. Okay, so the thing to keep in mind about card problems is that they are about constructing a hand as a sequence of choices. And so then you want to be multiplying, because it's a sequence of choices, number of opportunities. Okay, so here we're going to introduce probability diagrams, which are also called trees. So a driving test can be taken 3 times. What does the tree look for this? Every time you take the test, you can either pass or you can fail. So here's the start, the root of the tree. The first time you take the test, you can pass it or fail. 70% pass, which means 30% fail. Okay. After you've taken the test the first time, if you pass, you're done. The second time, you can take it again, and you can pass or you can fail. 40% of people taking this test the second time fail, so 40% and 60%. And you can take the test a third time. 80% of people who take it the third time fail, which means that 20% of the people who take it the third time pass. So this is a probability tree. The outcomes are the vertices of the tree, and then above each edge, you put the probability that you're interested in. Okay, and so this is the probability tree. So what's the probability of failing the first time and then passing the second time? That means I want the probability of this path, fail and then pass. And again, that's a sequence, right? And then, that means we're doing a sequence of things. And whenever you do a sequence, you multiply. So 0.3 times 0.8, which is, 0.3 times 0.6, which is 0.18. We just multiply the probabilities together to get the probability of that path. What's the probability of failing all 3 times? Well, that's this path through the tree, fail, fail, fail. And so that'll be 0.3 times 0.4 times 0.8, which is 0.096. Okay, what's the probability of passing? Well, there are 3 cases here. And keep in mind that cases are addition, right? So sequence is multiplication, cases are addition. What are my 3 cases? I could pass the first time, or I could fail and then pass, or I could fail, fail, and then pass. Right? So those are the 3 cases. Note that the word that joins these together is the word or. I could do this or this or this, right? That's the addition problem. If the process involves and then, right? First I do this and then I do that, then that's the multiplication principle. So what's the probability of passing on the first time? 0.7. Failing, then pass, we calculated that, that's 0.18. Failure, then pass, that's 0.3 times 0.4 times 0.2, which is 0.12 times 0.2, 0.024. Oof, I should have done that before. So 0.3 times 0.2 times 0.4 is 0.024, good. So if we add these together, what do we get? We get 0.904. So that's one way to think about it. This is 3 cases. But keep in mind, there are 4 cases total, right? You can fail or pass on the first time, or fail, then pass, or fail, fail, and then pass. Right? This we calculated in problem 3. These 3 together, right? That's what we're asking in problem 4. What's the probability of passing? So what has to happen? Well, one of these 4 cases has to happen, right? Either you fail the test, or you pass it the first time, or you fail and then pass, or you fail and then pass. So 0.096 plus the probability of passing has to equal 1. So what is this? 1 minus 0.096, which is in fact 0.904. So these two things, right, passing and failing, are complements. Right? You do either one or the other, but you don't do both. And what's the sum of the probability of complements? Well, you have to do one or the other, right? So probability of pass plus probability of fail, that has to be equal to 1. So if I can figure out this probability of failing, I can figure out the probability of passing just by taking 1 minus that, and then I don't have to deal with all these cases. Great. So probability tree can help in figuring things out, but keep in mind the difference between cases and sequences. One is addition, one is multiplication, and complements are useful. Okay, finally, 3 bakeries: Jane's Donuts, Andrew's Bakery, and Morgan's Baked Goods. And we have this table. So the first row is a percentage of all donuts that were made by the bakeries. The second row is percentage of donuts made by that particular bakery that were chocolate donuts. So what this is saying here is that 50% of all donuts were made by Jane's Donuts. Of all the donuts that Jane makes, 10% of them are chocolate. So we can present this in a probability diagram. My tablet has suddenly decided not to work, which is not good. Okay, so hang on a second. I need to stop sharing and deal with this issue. Okay, are we back? Nope. Okay, it's back. Sorry about that. Sometimes the tablet gets a little goofy. So we'll go back to sharing screen. 271 in class, that's this. There we go. So now we've got 3 bakeries: Jane's Donuts, Andrew's Bakery, Morgan's Baked Goods. And so what's our probability tree look like? Well, Jane, Andrew, and Morgan, 50% are by Jane, 30% are by Andrew, 20% are by Morgan. And then we can break up their output for each bakery into 2 categories: chocolate and not chocolate, right? Either they make chocolate ones or they make not chocolate ones. I'm using the symbol from the logic section for not. So 10% are chocolate from Jane, 90% are not chocolate, 20% are chocolate from Andrew, so that means 80% are not chocolate, 60% of Morgan's are chocolate, which means 40% are not. So there's a probability tree. That's one way to present this data. Another useful way to deal with this kind of data is just assume there's some large number of donuts were sold total if we're trying to figure out probability. So assume 1,000 donuts were sold total. So that would mean that Jane made 500 donuts, Andrew made 300 donuts, and Morgan made 200 donuts. How many chocolate donuts did Jane make? Well, 10% of her donuts are chocolate, so she made 50. 20% of Andrew's are chocolate, so he made 60. 60% of Morgan's are chocolate, so 120. Morgan made more chocolate donuts than Jane and Andrew combined, even though Morgan made many fewer donuts total. So that's another way to think about how to present the data. So if a donut is chosen at random, what's the probability that is chocolate and made by Andrew? There's two different ways to answer that. Chocolate and made by Andrew in the diagram is this path, right? Made by Andrew and then chocolate. So probability chocolate made by Andrew would be 0.3 times 0.2, which is 0.06. If we do it this way, Andrew's made 60 chocolate donuts out of 1,000, 0.06. So it's the same thing, just a slightly different way to calculate it. If a donut made by Andrew is chosen at random, what's the probability that the donut is chocolate? Well, that's exactly what this number is here, right? So if we're talking about a donut made by Andrew, that means we're at this point in the tree, right? We know that the donut was made by Andrew. What percentage of donuts made by Andrew are chocolate? 20%. So 0.2, or you could think of that as being 60 over 300, which is the same thing. Andrew makes 300 donuts, 60 of them are chocolate. If a donut is chosen at random, what's the probability that it's chocolate? So this has got three cases. So if we're dealing with a probability tree, that's a little bit tricky. Well, it's not tricky, it's just a little tedious. This, and this are your three cases. Calculate the probabilities for each of those and add them up. Another way to do that, which I find a little bit easier, is how many chocolate donuts were made? And that's just adding up this line. So 120 plus 60 plus 50 is 230 donuts. So 230 chocolate donuts were made. So if you want to go with the tree, you have to consider the three cases, each bakery. If you just go with 1,000 donuts made total, then 230 over 1,000, which is 0.23. 23% of all donuts were chocolate. And finally, if a chocolate donut is chosen at random, what's the probability that was made by Andrew? Well, there's 230 chocolate donuts, and 60 of them were made by Andrew. So 60 out of 230, and I'll write that so it's actually legible. You can also get that from this tree. You just have to figure out what's the probability that Andrew made a chocolate donut, which is 0.06. And then you have to divide it by the probability of getting a chocolate donut, which is the probability that you get a chocolate donut from Jane, which is 0.5 times 0.1, plus the probability that you get a chocolate donut from Andrew, which is 0.3 times 0.2, times 0.2, that's a point, plus the probability that you get one from Morgan, which is 0.2 times 0.6. So that's the three cases that we have there. If you add those up, it becomes 0.23. So the probability that we get from a chocolate donut chosen at random, this is probability that you get Andrew and chocolate divided by the probability that you get a chocolate donut. For me, these kinds of questions are easier to do if I just assume that there's 1,000 donuts and then figure out all the numbers and then do division, but you can get it all from the table. Okay, so that's the introduction to probability.